Hey everybody. So in this video, we're going to start trying to get a little bit used to graphing in 3 dimensions, which is a whole different ballgame than 2 dimensions, obviously. And it's harder to picture and certainly trickier to draw. So we're going to try to get our heads around some of the ideas. And there's really no substituting for just doing a bunch of it. We are lucky to live in an age when we have computers that can do it for us, so that we can get really nice, beautiful pictures rendered for us. However, just like graphing in 2 dimensions, right? We know that we can use a computer to graph in 2 dimensions. If you haven't spent time graphing quadratic functions or rational functions or the square root function or exponential functions, you probably don't have as deep of an understanding of what they're actually telling us and what their behavior means, right? And so even though we don't have to use pen and paper to graph, it is a valuable exercise in us understanding. So that's one of the big reasons we're going through this. But what's wonderful is we can then supplement that exercise by looking at a picture on a computer screen, which I will do in this. So we're going to try to get some techniques for graphing these kinds of things. So I'm going to start with something in 2 dimensions, just to make a parallel, make a metaphor for what we're going to do next. Let's look at just the graph of, say, y equals 3. Okay. Now, remember what the graph of an equation is. The graph of an equation is the set of all points that sets the equation, that satisfies the equation. So if I'm graphing this equation in our traditional xy plane, all that needs to happen to satisfy this equation is that y be equal to 3. So if that's 3 right there, we extend this, pretend that's a horizontal line, we extend this horizontally and get the graph of this, right? In other words, we're saying the value of x doesn't matter to this equation, so all values of x are acceptable, okay? So we sometimes get a similar thing. Well, we do get a similar thing if we have a similar idea in 2 dimensions. Sorry, 3 dimensions. So let's look at this graph. Okay. Now, if I'm talking about graphing, see if I can use some of these tools in 2 dimensions, right? We probably know what this graph is, right? This is going to be a circle centered at the origin. Oops, that was supposed to be a circle. Centered at the origin with radius of 3, right? So let's look at the example I just gave a second ago. If we have a circle centered at the origin, I didn't know the screen would start doing that, and I'm not sure why it did. Let's make that stop. Let's see. All right. Sorry about that. That was a new one for me. So just like in 2 dimensions, when we're looking for x-y pairs that satisfy the equation y equals 3, since x doesn't appear, x can be anything. And so our solution is all of the coordinates with any x value and a y coordinate of 3. Well, now, in 2 dimensions, this is a circle, but if I add the 3rd dimension, if I'm actually talking about a graph in 3 dimensions, what I'm saying to this is I'm looking for pairs where the x and y coordinates have to satisfy this equation, right? But the z coordinate can be anything, right? So the x and y coordinates come from this equation, but our z coordinate can be anything. So just like we extended this red line horizontally to encapsulate all the x values, we're going to extend this circular shape in the z direction, right? Which will give us, oops, there we go, this graph, right? So it disappears because we're looking perfectly down it, but there's a circle, and when we extend it in 3 dimensions down the z-axis, we get what we call a cylinder, right? So generally, we probably think of cylinders as being circular shapes like this, extended, but it really can be any shape that's extended along in one of the directions. Okay, let's look at another one of these. This time, let's look at the graph of z minus y squared equals 2, right? This is a very similar idea. We're looking at two variables in a three-dimensional space. And so x, in this case, doesn't affect whether or not points satisfy this equation, right? Again, similar idea. X can be anything. Y and z have to be such that they satisfy this equation. So I'm just drawing those arrows to mean the values of these are going to be all the values of x, z, and y that satisfy this equation. And we know the shape that those have, right? So if I think of, oops, this is supposed to be a plus. If I think of y as my input and z as my output, if I'm only looking at the y and z axes, this should look like a parabola. But then I extend this along the x direction, right? Again, just like extending that horizontal line in the previous example. So let's look at that one now in our graph. So let's see, let's orient this. Here I'm looking at it, the green is the y-axis, the blue is the z-axis. But if I turn to look where I can see the x direction, I see that I've taken that parabola and extended it along the x direction. And this is another cylinder, it's a parabolic cylinder that we're looking at here, right? So these are very nice. At any value of x, for instance, let's take, for instance, let's take x equals 5. Yeah, it goes that far, right? We can see the intersection of that plane. That's all the points where x is equal to 5. They all lay along a parabola, right? You can see the shape, the intersection that plane is making with that surface, right? These are things we call traces. We take a slice and see what the cross section is. When we take a slice, what we can think of is we're taking that variable out of the equation, right? We're thinking of that variable as a constant, and so it doesn't change. And we see how the other two variables, how they relate at that value, right? So let's do another one here. For instance, with this same graph, if I took a slice, let's say at y or at z equals 5, what do I get? The intersection is two parallel lines. Well, why is that? Let's look at our equation. We started out with z minus y squared equals 2. X can be anything, but what we know along this, when we intersect with the plane z equals 5, we get 5 minus y squared equals 2, which is equivalent to saying y squared equals 3, or y equals plus or minus 3. Right? Well, if y is plus or minus 3 and x can be anything and z has to be 5, what are we left with? We get in the xy direction, so let's see, let me turn this, oh, I want to turn it the other, oh boy. There we go. Now we're looking at it where the red axis is the x-axis, is in the positive to the right, and y is pointing up. Notice the intersection, this place where the red where the red and the blue, let me just point it out, right? There's a line. Oh, right, sorry, I wrote sorry, this is supposed to be the square root of 3, obviously. I took y squared equals 3, and then we get to y equals plus or minus the square root of 3, which is about 1.7 and negative 1.7, right? These intersections are these two horizontal lines, just like in the first example, right? So x can be anything, we extend this way. Z is locked in at 5, right? We can't see it from this perspective, but when we turn, we see those two intersecting lines are at a single value of z. So that's a less interesting trace. It's just these two pairs of lines. Okay, let's do a little bit, let's complicate things now a little bit. Let me erase what we've got and start with something clean. Where are you at? There we go. All right, let's look at a more complicated sort of equation. Let's look at x squared over 4 plus y squared over 16 plus z squared over 9 equals 1. Okay, so now we don't have this feature where we have one variable gone. It's not going to be the same kind of cylinder extended in one direction. They're all going to have some interplay with each other. But we can use this idea of taking a trace, a slice of this thing, to see what it looks like. So for instance, let's try this. Let's imagine taking the slice at x equals 1. So this is a plane, right? There's a plane, x equals 1, right? Just that sheet where every x coordinate is 1 and y and z can be anything else. But let's see what it does to this equation. If I put in 1 for x, I get 1/4 plus y squared over 16 plus z squared over 9 equals 1, or y squared over 16 plus z squared over 9 equals 1 minus 1/4, right? That's 3/4, but I want to leave it like this for now. You might recognize this as the equation, an equation for an ellipse, right? To put it in traditional form, we'd have to do a little more work, but this is pretty close to know that this is going to be an ellipse. And in fact, let's generalize this a little bit. Let's, instead of saying x equals 1, let's just use k to be any constant. Then we get this, for any constant value of x, y squared over 16 plus z squared over 9 is equal to 1 minus k squared over 4. So the larger k gets, the smaller the right-hand side gets. So we're getting smaller and smaller ellipses as k gets larger. Also notice the left-hand side has to be at least 0. It can't be negative because y squared and z squared are going to be positive, which means k can't be bigger than 2, because once k is bigger than 2, this right-hand side becomes negative and there's no points that satisfy that. So what that means is, as k goes from 0 to 2, we're getting smaller and smaller ellipses, and we get the same thing from 0 to -2, because the k squared does the exact same thing, right? Well, also notice, I can play the same game with all of these variables, right? It just changes a little bit about the ellipse, about what are the values in the denominator, and how quickly the size of these ellipses change. So let's take a picture. Well, let's draw this. For instance, if we think of y and z, right? Y squared over 16 and z squared over 9. What I'm saying is, for different values of k, we're going to get ellipses that are getting smaller and smaller and smaller, right? So each of these would be a different value of k, a smaller and smaller value of k. When k equals 2, there's only one there's only one solution to the equation. Y squared over 16 plus z squared over 9 equals 1 minus 1, or 0, is when y and z are 0. So it's just this point there. So let's see that with a little more clarity in the graph. So now I want to look at this one. So here is our shape. So I'm looking down the x-axis right now. So let me turn it around so it's the right orientation. We've got y is positive to the right, z is positive up, and let's add in the plane x equals, here's x equals 0. And I'm going to start making it bigger and look at these intersections. That dark circle, the outline of that is the intersection. And as I go closer and closer to 2, it's getting smaller and smaller. And then right at 2, we can't really see it, but there is a point. And then now that I'm larger than 2, there's no more intersection, right? If I look to the side, I see that I've gone beyond it, right? And then I can come back. You see right at 2, we're just touching the side of it, and we have been taking all these slices down the side. And a similar thing happens as I go in the negative direction. We can see it going down down there, right? Let's try a plane in a different direction. Let's look at z equal to something. So now I'm looking down the z-axis, and I'm getting the same shape more or less. It's not exactly the same ellipse, but we're getting these traces that are all ellipse shaped. By ignoring the z, we end up with just the equation x squared over 4 plus y squared over 16 equals some constant, which is, again, the equation of an ellipse. So that's another example of these traces. Okay, let's do one more, maybe two more, we'll see. Let's do at least one more. Okay, I'm going to erase this one. Oops. And we'll do something that might be a little less familiar. Let's do z equals y squared minus x squared. Okay. So we're going to do a couple of different traces in different directions. I'm going to start by picking, let's say, traces in the x direction, meaning let's set x equal to some constant k. Well, if x is equal to a constant k, then z is equal to y squared minus k squared. So the graph of this should just be, right? If we were graphing the y-axis and the z-axis, if we pretended this was just a two-dimensional problem and k was just some constant, this is just going to be a parabola, right? And we've got a k squared, so it's always going to be a positive number below the, so we're taking a parabola and dipping it down below the in this case, y-axis, right? And depending on the value of k, as k gets larger, it's going to dip further and further down, right? A vertical shift. So that's like three traces I'm drawing for different values of k, right? Maybe down 2 and 3 and 4 and so forth, okay? What about what happens in the other direction? What if I let z equal a constant, right? What does my equation become then? K equals y squared minus x squared. Let's think for a second about what this might look like if you don't recognize what this kind of equation is. Again, k represents a number here, so for each fixed number, I want to come up with the shape of this thing. So let's maybe solve this and look at it in maybe an easier way to see it. Y squared equals x squared plus k, which means y is equal to the square root of x squared plus k, or y is equal to the negative square root of x squared plus k. Okay. Well, for the moment, let's imagine that k is positive and get an idea of what this graph is going to look like. So here's my xy coordinate system. Let's look at the top one first, the positive portion of this, right? So looking at this one first. Well, first of all, if x gets really, really large, k doesn't matter very much, right? If x is 1 billion and k is 10, you take 1 billion squared, add 10 to it, and take the square root, you basically get 1 billion back. In other words, the graph looks very similar to y equals x. They're almost the same, right? Because if x is big and we square it, add a little bit and take the square root, we're getting back almost the same thing, right? 100 squared plus 1, take the square root of that, you get just over 100. But also, if you put in negative values for x, you get almost the same value back except positive. In other words, this is very similar to the absolute value of x when x is large, right? So there's the absolute value. Again, I'm looking very similar to it. But what happens as we get closer and closer to x equals 0, this k matters a lot more. And what happens is, as x equals 0, we're going to hit the x-axis at some positive number. And so this graph will look something like this, right? And in the negative direction, it's going to look the same but reflected, right? Further away from x equals 0, it's very close to the absolute value or the negative absolute value. But right near 0, all of a sudden that k starts to matter. And we bend away from that graph, right? What about if k is negative? So let's do this. The red is for k greater than 0. Let's think about k less than 0. It's negative. Well, a similar idea happens, except now we're subtracting something. So instead of being almost the same, again, I'm thinking of x very, very large. I square it, take something away and take the square root. I get almost the same thing back, only it's a little bit smaller. And this time, I'm almost the same as that line, but I'm just smaller than it. In the negative direction, I'll be just above it, right? So, right, the red one has to be just above it because we're adding something. The blue one's just below it because we're subtracting something. The negative, we just get the reflection of that, right? The other thing that happens is if we're subtracting a number here, we can't make x too small. For instance, x can't be 0 because then we have 0 minus something. We're trying to take the square root of a negative number, which we can't do. So our domain, we can't get any smaller than the square root of k. So let's pretend that's about right here. And so our graph, right, it's not technically a function anymore. Well, the top half is one function, the bottom half is the negative half of this. And then the exact same thing happens for the negative values of x. We get this kind of shape. Okay, these are called hyperbolas. So when we intersect this original equation, z equals y squared minus x squared, with values of z, if the values of z are positive, it should look like this red graph. And if the values of z are negative, it'll look like this blue graph. It just changes which axis it kind of goes along, right? Where this curve intersects. Does it intersect the x-axis or the y-axis, right? And we get a similar thing if y is a constant, except it'll be a parabola facing down because we put a constant in for y and we get k squared minus x squared is a parabola facing down. So let's go to our graph and take a look at all this. All right, so now I'm looking at this one. All right, so the shape is quite a bit different. It's a very, let me see if I can zoom out so we can, this isn't a great view. I don't know how to change it exactly. It's this saddle shape, right? So it's kind of an odd shape to look at and imagine. Let's intersect it with x equals a value. And notice what we're getting. So it doesn't draw the plane everywhere, but we predicted that we would get parabolas that are dipping down below the y-axis. And that's exactly what we're seeing here, right? And if I change the value of k, it just changes how far down that dips. Excuse me. On the other hand, let's do y equals a constant. Remember, we said we would get downward facing parabolas and they would be raised above the x-axis depending on the value of k, and that's what we're seeing here. And then finally, let's do intersections with z equals a constant. And there we see that intersection, which here is, right, this, I'm just going to draw this little piece of it, right? It's this intersection. You can follow it all the way along. And if I change the value of k, we'll see it takes on different shapes, right? So now the intersection has moved in the other direction. This is the negative values of k, which are along, oh, I've got it turned here. Let's turn it the way we had been looking at it. So here, all right, there I've got the x-axis in. The positive is going to the right and the y-axis positive is going up. For negative values of k, we see that the intersection is along the x-axis. When k is equal to 0, we see it actually just becomes the absolute value function plus or minus. And then when k is positive, it's that hyperbola shape intersecting with the y-axis, okay? So I know if you're new to graphing these things, it's a whole lot to think about. I'm going to encourage you to play with some of the software that I've shown you here, that or other graphers that you find, and graph some of these surfaces and see if you can predict what intersections are going to look like, and then confirm your predictions with the software. Okay, that is going to do it for this one. Yeah, that'll do it for this one. I will see everybody next time.